Hello, I'm Dr. Steve Warner, and today I'm going to talk about complex numbers. A complex number has the form a plus bi, where a and b are real numbers, and I is the square root of -1. So here are some examples. 2 plus 3i, 3 halves minus 2i, negative pi plus 2.6i. Okay, notice that we have a real number plus or minus another real number times I. These numbers do not have to be integers. They could be things like pi and 2.6. Here's another example, 5i. That's a complex number because it could be written as 0 plus 5i. So here a is 0 and b is 5. But we'll usually just abbreviate that as 5i. And we call that kind of number a pure imaginary number. The number 17 could be written as 17 plus 0i, and we identify that with a real number. 0 can be written as 0 plus 0i, but we'll usually just write that as 0, and that's the 0 for the complex number system. The square root of -9, well, that's 3i, because the square root of 9 is 3, and the square root of -1 is I. And similarly, 2 plus the square root of -2 is 2 plus root 2 times I. We could pull negative signs out of square roots as i's. Let's look at an example. After solving a quadratic equation by completing the square, it was found that the equation had solutions x equals -3 plus or minus the square root of -16b squared, where b is a positive real number. Which of the following gives the solutions as complex numbers? Well, what we're really interested in here is just simplifying that square root, the square root of -16b squared. So the square root of 16 is 4. The square root of b squared is b, because b is positive. And the square root of -1 can be changed into I. So we get 4bi. So the answer to the question is actually -3 plus or minus 4bi, which is choice B. Powers of I. Okay, remember that I is the square root of -1. Let's start raising I to various powers. I squared. In other words, the square root of -1 squared. Well, when we take a square root to the power of 2, they just cancel, and we get -1. I cubed is just I squared times I by basic law of exponents. So that's -1 times I, which is just -I. I to the 4th, well, we could think of that as I squared times I squared, which is -1 times -1, or +1. I to the 5th, well, that's I to the 4th times I. Oh, that's just 1i, which is I. And as it turns out, powers of I have a repetitive pattern. So I to the 0 is 1, I to the 1 is I squared is -1, and I cubed is -I. This row gives all the unique answers. After that, it keeps repeating. I to the 4th is 1, then I to the 5th is the same as I to the 1st, which is I. I to the 6th is the same as I to the 2nd, which is -1, and so on. This pattern keeps repeating. There are only 4 unique answers, and they repeat over and over and over again. So if we wanted to evaluate I to a power, we can simply look at the remainder when we divide the exponent by 4. Let's look at an example. I to the 73. Well, to figure out what that is, let's divide 73 by 4 by hand. 4 goes into 7 once, with 3 left over. 4 goes into 33, 8 times with a remainder of 1. The important thing is that the remainder is 1. So I to the 73 is exactly the same as I to the 1, which is just I, and that's choice D. I should mention this could also be done quite quickly in your calculator. You could type I to the 73, but your calculator does do something funny sometimes. The method that it uses to compute this is an approximation method that often writes 0 in a weird way. For example, if you type this on your TI-84 calculator, you might get negative 2.3 e negative 12 plus I. This expression here is scientific notation for a really tiny number, which is essentially 0. So in other words, this is the same as 0 plus I, which is I, and that's what we got when we did it by hand as well. Addition and subtraction. We add two complex numbers by just adding the real parts and adding the imaginary parts separately. So here's the formal definition of how to add. A plus bi plus c plus di is a plus c plus b plus di. But again, that just means we're adding the real parts and adding the imaginary parts independently, and we do the same for subtraction. So let's look at an example. The sum of the complex numbers 2 minus 3i and negative 5 plus 6i is what? Well, if we add the real parts, 2 plus negative 5 is negative 3, and then we add the imaginary parts. Be careful to include the sign. Negative 3i and 6i is positive 3i, so that's choice D. Another example. When we subtract 2 minus 3i from negative 5 plus 6i, we get which of the following complex numbers? Okay, so I could do this a couple of ways. I could do negative 5 minus 2 and then do 6 minus negative 3. The double negative might be a little confusing, so let me start by distributing that minus sign. Notice that I get negative 2 plus 3i when I remove the parentheses. Negative 5 and negative 2 is negative 7. 6i and 3i is positive 9i. That is choice B. Okay, now let's talk about multiplication. The definition of multiplication might look a little complicated. A plus bi times c plus di is ac minus bd plus ad plus bc times I. But this is equivalent to just multiplying two polynomials and replacing I squared by negative 1. For those of you who like foiling, you could do it that way. So let's look at this example. 2 minus 3i times negative 5 plus 6i. When we multiply the two firsts, 2 times negative 5, we get negative 10. When we do the lasts, we get negative 3 times 6 is negative 18 I squared. The outers and the inners give 12i for the outers and plus 15i for the inners. Now, since I squared is negative 1, this actually becomes negative 10 plus 18. And here we have plus 12 plus 15 times I. So the final answer is 8 plus 27i, and that is choice E. The conjugate of the complex number a plus bi is the complex number a minus bi. In other words, we just changed the sign in front of the imaginary part of the complex number. So the conjugate of negative 5 plus 6i is negative 5 minus 6i. And the conjugate of 3 minus 2i is 3 plus 2i. Note that when we multiply conjugates together, we always get a real number. In fact, a plus bi times a minus bi is a squared plus b squared. The first, a times a, give you a squared. The last, bi times negative bi, is negative bi squared, which becomes positive b squared. And the outers and inners always cancel because you get negative abi for the outer and plus abi for the inner. So you don't actually have to remember that. You could just remember that when you're multiplying conjugates, you get a positive real number, which is the sum of the squares of a and b. This observation can help us to divide complex numbers pretty easily. So the trick is to divide two complex numbers, you take the conjugate of the denominator and multiply both the numerator and denominator by this conjugate. So let's do the denominator first, because we just get 2 squared plus 3 squared in the denominator. And in the numerator, we get 1 times 2 is 2, minus 5 times 3 is 15, plus 1 times 3 is 3, plus 5 times 2 is 10, I. So that simplifies to negative 13 plus 13i over 4 plus 9, which is also 13. Be careful how we split this up. 13 goes into negative 13 negative 1 times, and 13 goes into 13i 1i times. So the final answer is negative 1 plus I, which is choice B. The absolute value of the complex number a plus bi is the square root of a squared plus b squared. So for example, the absolute value of 2 plus 3i is the square root of 2 squared plus 3 squared, which is the square root of 4 plus 9, or the square root of 13. The absolute value of 3i, well, 3i could be written as 0 plus 3i, so we get the square root of 0 squared plus 3 squared, which is the square root of 9, which is 3. And the absolute value of negative 5, well, that could be written as negative 5 plus 0i, which is the square root of negative 5 squared plus 0 squared, which is the square root of 25, or 5. Note that for real numbers, this definition of absolute value agrees with the definition for absolute value that we already know for real numbers. Geometrically, we can plot the complex number a plus bi as the point AB. So that's this point right here. We go right A, up B to plot the point a plus bi in what's called the complex plane. The absolute value of a plus bi is this distance from the origin to the complex number, or equivalently from the origin to the point AB. Let's draw a picture of the complex number 3 plus 4i and find its absolute value. So first, here's the complex plane. This is the real axis, and what we normally have as the y-axis is the imaginary axis. 1, 2, 3, 1, 2, 3, 4. So here's the point 3, 4, which we identify with the complex number 3 plus 4i. To plot that point, note that we went to the right 3 and up 4, and the absolute value is this distance. Many of you might recognize this as a 3, 4, 5 right triangle. So right away we can see that the absolute value of 3 plus 4i is 5. If you don't see that right away, you could either use the Pythagorean theorem or the definition of absolute value of a complex number, which leads to the same exact computation. So the absolute value of 3 plus 4i is the square root of 3 squared plus 4 squared, which is the square root of 9 plus 16. That's root 25, which is 5, as we found before.